learned how to trace curves, not only from the point of view of giving it a finishing touch in calculus, but also a pending topic in calculus, which is area calculations, where we are going to be compelled to trace curves, to draw them appropriately, so that we can figure out how to compute areas, etc. Now, some very basic things, no rocket science really involved, although this entire business of curve tracing can be very intricate. There are a host of things that you can learn and do with it, but at this level, at your level, there is a basic premise with which you must be familiar, you must be comfortable, and which is why I will give you a very basic informal introduction to curve tracing. But even before I do that, one thing that I want to communicate, which is a formal notion of asymptotes. We've looked at asymptotes in light of hyperbola, but now in a very general sense, given a curve, how do we find asymptotes to the curve, if at all there are, right? So if I talk of a curve y equal to fx, if I talk of a curve y equal to fx, and say this is an inclined asymptote, let me get general about it. If say this is an inclined asymptote to the curve, then what it really means is, this is the curve. Say this line referred to as y equal to mx plus c, and what it really means is that this p into this and this q is the separation between the curve and the asymptote. PQ is the separation between the curve and the asymptote, and as x tends to infinity, or let's say plus or minus infinity, let's say very far away from the origin, PQ must tend to 0. PQ must tend to 0. As x tends to infinity, PQ must tend to 0. That's the whole idea really. Which means, theoretically speaking, this line becomes a theoretical tangent very far away from the origin. It becomes a theoretical tangent, right? Now, the length PQ is what? Y of the straight line minus y of the curve. For a given x, y of the straight line would be mx plus c, right? That means PR would be mx plus c, and y of QR would be fx, right? So PQ is mx plus c minus fx. Right? I'm seeking to find m and c. Such that limit as x tends to infinity, mx plus c minus fx is 0. I want to find m and c such that mx plus c minus fx is 0. Then y equal to mx plus c will be an inclined asymptote to the curve, right? Now, if I say divide by x throughout, right, then this will become like a c by x, this will become m, this will become fx by x, right? And as x tends to infinity, the c by x obtained out of dividing by m will tend to 0, right? Because c and m are finite numbers, right? So it becomes, on dividing by x, it becomes m plus m minus fx by x, as x tends to infinity is 0. I hope you all realize this. On dividing by x, this will be m plus c by x minus fx by x as x tends to infinity. And the c by x would tend to 0 as x tends to infinity. So then we have limit m minus fx by x as x tends to infinity is 0, leading to m equal to limit fx by x as x tends to infinity. Right? If this limit exists and is finite, then there is an asymptote. Now, what about c then? So once you have found m, go back to this equation. Then the c can be found from this limit. C would be limit fx minus mx as x tends to infinity. That will be c. That will be c. M you can plug in from that limit and obtain this limit again if c is finite and exists. Then, and if this limit exists, then y equal to mx plus c would be an inclined asymptote to the curve. Got me? So essentially what really happens is that very far away from the origin, the curve becomes synonymous with the line y equal to mx plus c. That is what is really happening. Then y equal to mx plus c is referred to as an inclined asymptote to the curve. Now, can I wipe this off? Now, there is a notion of what's called a vertical asymptote. So that was an inclined asymptote. We have what's called a vertical asymptote. Say I have a curve y equal to fx equal to 1 by x minus a. Y equal to fx equal to 1 by x minus a, suppose is a curve, right? In this case, this is the line x equal to a where fx is undefined. This is x equal to a where fx is undefined. Right? X equal to a where fx is undefined. Now do you realize that as x tends to a from the greater than a side, then fx would tend to plus infinity. Right? Fx would tend to plus infinity. As x tends to infinity, fx would tend to 0. Fx would tend to 0. Isn't it? And if you look at f dash x, what is f dash x? Is minus 1 by x minus a whole square, which is less than 0 for all x, means fx is monotonically decreasing. There is no stationary point. There is no stationary point. So now, as x tends to a from the greater than a side, then fx tends to infinity. As x tends to a from the greater than a side, fx tends to infinity. As x tends to infinity, fx tends to 0, and the function is continuously decreasing. Therefore, as x tends to a, this is a, then fx tends to plus infinity. And as x tends to infinity, fx tends to 0. Right? So this x equal to a flushes with the curve, again very far away from the origin. This x equal to a starts to flush with the curve very far away from the origin. And this x equal to a is referred to as a vertical asymptote. So if x minus a appears in the denominator of an expression, then x equal to a will be a vertical asymptote, So this is a vertical asymptote. And just to complete matters here, as x tends to a from the less than a side, this will be negative. Fx will tend to minus infinity. And as x tends to minus infinity, fx would again tend to 0. Right? And therefore, x tends to minus infinity, fx tends to 0, as x tends to a, fx tends to minus infinity, and so on and so forth. Yeah, please come in. Right? So this is the notion of a vertical asymptote. Right? If x minus a appears in the denominator, then there is a vertical asymptote, x equal to a. If x minus a into x minus b appears in the denominator, then two vertical asymptotes, x equal to a and x equal to b. If x square minus a square appears in the denominator, then x equal to plus a and x equal to minus a are two vertical asymptotes. This is the whole idea of a vertical asymptote. I must share and confess that what I am telling you is very laymanish, very preliminary, very basic. The concept of asymptotes is a lot more sophisticated than the manner in which I have communicated. But then, if you understood whatever I have communicated, then that will suffice for your level, right? It's just an oversimplification of the idea, but then the idea is a lot more elaborate than what I have just said. Can I wipe this off? Now, if I have a curve like this, y equal to, say, a linear expression ax plus b plus c by x minus d, kind of a thing. Something like this. One thing, it will have a vertical asymptote, x equal to d will be a vertical, because as x tends to d, this whole thing tends to infinity, right? So there is a vertical asymptote for sure. This will suggest that there is a vertical asymptote x equal to d. Not only that, this is because as x tends to d, y would tend to either plus or minus infinity. Y would tend to plus or minus infinity, isn't it? Depending on whether x tends to d from the greater than d side, it will tend to plus infinity. Less than d side, it will tend to minus infinity. Now, also realize that if x is very far away from the origin, as x tends to infinity, that means as this becomes larger and larger and larger, then the curve comes closer and closer to this straight line. Do you realize that? Because this becomes smaller and smaller and smaller. This becomes smaller and smaller and smaller as x tends to infinity. Therefore, the curve comes closer and closer to this line, y equal to ax plus b. Right? Comes closer and closer to the line, y equal to ax plus b. Therefore, the curve y comes closer and closer to ax plus b, and therefore, y equal to ax plus b must be an inclined asymptote. Y equal to ax plus b, therefore, will be an inclined asymptote, right? Is that okay or not okay? So if someone gives you an a curve like this, you can say x equal to d will be a vertical asymptote and y equal to ax plus b would be an inclined asymptote to the curve. So this was a very rudimentary understanding of asymptotes, but that's enough. Now let me get into all of the tools that you require for tracing curves at this level. Those have been communicated to you, but let me just formally state those things across. Okay. Now, so it's all about investigating the curve systematically, investigating the function whose curve you want to trace systematically. That's the whole business, right? Say y equal to fx is a curve. It's a function. Now, in your endeavor to trace the curve and therefore investigate the quality of this function, what would you start with? No. The basic thing you'll start with is the domain and range of the function, right? The values of x for which it's defined, the values of x for which it's not defined. I mean, if I had y equal to root 1 minus x squared, right? Then I know that it's defined for x lying between -1 to +1. That means no part of the curve exists to the right of x equal to 1. No part of this curve will exist to the left of x equal to -1, right? Therefore, this curve would be investigated only for mod x less than or equal to 1, right? So you would first want to check on the values of x for which the function could be described, right? So you know that this is your processing window. Within these values of x, you would trace the curve. You don't have to go hither and thither, run around helter-skelter to trace the curve for other irrelevant values of x. So the domain and range, the domain specifically will tell you the values of x that will be relevant towards drawing the curve, right? So one thing that you do is you do a domain and range. Right? The next thing, see, in the order of importance, the next thing that you would want to check is the roots, the values of x for which y becomes 0. Right? That's the second thing you want to check, right? The roots. Values of x for which fx becomes 0. Values of x for which fx becomes 0. That's the second thing that you want to check in your attempt to trace the curve. Clear? Check for symmetry. Check for special points. When I say special points, points where there is discontinuity, there is lack of differentiability, critical points. What are critical points? Points where dy dx becomes 0. Examine whether it's at a point where dy dx is 0, whether it's a local maxima or a local minima, or even if dy dx is 0, the function could be increasing or decreasing at that point, right? So in any case, points where dy dx becomes 0 will become critical to our attempt to draw a curve, right? So these are the critical points, points where dy dx becomes 0, right? Once you differentiate dy dx, then as an offshoot of this, you can also check points where dy dx is greater than 0, points where dy dx is less than 0. That means you would know the interval in which the function is increasing, the intervals in which the function is decreasing, right? Monotonicity, intervals of monotonicity would be discovered when you carry out these checks: dy dx greater than 0, dy dx less than 0. Sometimes the shape of the curve. How do you check the shape of the curve? d2y dx2. Check for this. If d2y dx2 in an interval is greater than 0, then it's a concave curve. If d2y dx2 is less than 0, then in that interval the curve is convex, right? So further refinement of the curve would come once you give it a shape. You know the function is increasing, but whether it's increasing in a concave manner or in a convex manner would be determined by the second derivative, sign of the second derivative. And therefore, if you did this, then as a consequence of this, you would also want to find points where d2y dx2 becomes equal to 0. this would in general mark points of inflection, points where the curve changes from concave to convex or convex to concave, right? This is points of inflection. Right? Check for symmetry. Symmetry. Now, if you find only even powers of x in that function, suppose in y equal to fx, say y equal to x squared plus x power 4 plus 1. There are only even powers of x. There are only even powers of x. Therefore, if x comma y satisfies this equation, then minus x comma y will also satisfy this equation. That means if x comma y be a point on this curve, then minus x comma y will also be a point on this curve. Yes or no? Right? Which means, see, x comma y is a point here, and minus x comma y is a point here. And what are these points? They are mirror images about the y-axis. Therefore, the curve would be rendered symmetric about the y-axis. So, if there are even powers of x, if there are only even powers of x, then the curve is symmetric about y-axis. If there are only even powers of x, then the curve is symmetric about the y-axis. Similarly, say I have y squared equal to x. There are even powers of y. That means if on this curve x comma y be a point on this curve, then x comma minus y will also satisfy this equation, isn't it? That means this is x comma y, and this would be x comma minus y. So if this is a point on the curve, then q will also be a point on the curve. And what are these? Mirror images about the x-axis. And if this happens, if there are only even powers of x, even powers of y, that will cause the curve to be symmetric about the x-axis. Even powers of y will cause the curve to be symmetric about the x-axis. So even powers of x, even powers of y will cause the curve to be symmetric about x-axis. And if there are even powers of x and y both, then the curve would be symmetric about the x as well as the y-axis, right? Now, you might want to, in certain cases, the function could be periodic with periodicity t, fundamental period t. Then all that you need to do is trace the curve only from x equal to 0 to x equal to t, and then cut and paste that curve, copy and paste that curve, isn't it? If you know that the curve is periodic with periodicity t, and you know the trace of the curve, let's say from 0 to t, you know how to trace the curve from 0 to t, then don't do anything else. Then simply copy and paste this portion to reflect periodicity. And so on and so forth, right? Say for example, y equal to 2 to the power fractional part of x. Its periodicity is 1. It will inherit periodicity from fractional part of x. Therefore, this is a function which is periodic and has periodicity 1. Hey, what's the graph of 2 to the power x? The graph of 2 to the power x is this: x equal to 0, x equal to say log 2. Right? Log 2 to power x will be 1 when x log 2 is x equal to 0 is 2 when x is 1, right? Now this curve y is 2 to power x, fractional part of 2 to power fractional part of x. Realize that when x lies from 0 to 1, this is the trace of the curve, right? When x lies from 0 to 1, when x lies from 0 to 1, this is the trace of the curve, right? To the inclusion of 0 but to the exclusion of 1, right? Now when x lies in the interval 0 to 1, fractional part of x will be the same as x. When x lies in the interval 0 to 1, fractional part of x will be the same as x. So the graph of 2 to power x will be the same as 2 to power fractional part of x in the interval 0 to 1. Yes or no? When x lies from 0 to 1, then fractional part of x will be the same as x, right? So the graph of 2 to power x will be the same as graph of 2 to power fractional part of x. So this graph, which includes 0 but excludes 1, this is the graph of 2 to power x in the interval 0 to 1, right? In the interval 0 to 1, this is the graph, right? Now this will be the same as 2 to power fractional part of x. Why? Because in this interval 2 to power x and 2 to power fractional part of x mean the same. Now you know that this function is periodic and has periodicity 1. So then all that you need to do is, you don't have to investigate other intervals. You say from 1 to 2, the same part will get reflected, not reflected, copied. So just draw the graph from 0 to 1 and copy paste, given that the periodicity of this function is 1. This is what you need to do, right? So if a function is periodic, then just draw the graph in over a length equal to 1 period t, and then copy paste over the required domain. Over the required domain, copy paste the graph, right? So sometimes you want to check for periodicity if the function is periodic. If you find in a given function, if you replace x by y and y by x, and it remains, the function y equal to fx remains unaltered, then realize that if h comma k lies on this, then k comma h will also lie on the function, on the graph. If h comma k lies on this, then k comma h will also lie on the graph of the function. Yes or no? That means on replacing x by y and y by x, on replacing x by y and y by x, if this function remains unaltered, let's say for example x cubed plus y cubed equal to 3xy. See, in this, if you replace x by y and y by x, nothing changes. That means if h comma k lies on this, then k comma h will also lie on this, right? But h comma k and k comma h are what? They are? Yes, they are mirror images about the line y equal to x. If p is h comma k, then q would be, k comma h would be the mirror image of p about the line y equal to x. Right? Isn't it? Therefore, this function which remains unaltered, this graph which remains unaltered on replacing x by y and y by x, must enjoy symmetry about the line y equal to x. Must enjoy symmetry about the line y equal to x. Right? See, x cubed plus y cubed equal to 3xy will actually be symmetric about y equal to x. So, if this happens, then we say it's symmetric about y equal to x. Right? So far so good? Very good. Can I wipe this off? And then of course, check for asymptotes if any. Check for asymptotes if any. And if there are asymptotes, then you realize you first draw the asymptotes and then draw the curve. Like we did in hyperbola, remember? We first drew the asymptotes, it was easier then to trace the curve. So if there are asymptotes, then for the sake of getting more accurate looks of the graph, first draw the asymptotes and then trace the curve. That's the first thing, if there are asymptotes, right? Vertical or inclined, as the case may be. All of you understand this? Right? Also, if x comma y be a point on the curve satisfying the equation, and you find that minus x comma minus y is also a point on the curve, you find that minus x comma minus y is also a point on the curve, then what it really means is the curve would be symmetric about the origin in opposite quadrants. The curve would be symmetric about the origin in opposite quadrants. See, x comma y and minus x comma minus y are symmetric points with respect to the origin, and they lie in opposite quadrants. Why? Because the midpoint of x comma y and minus x comma minus y is the origin, right? So it must be symmetric about the origin and opposite quadrants, first and the third, second and the fourth, right? Have you all understood this so far? Now the next thing I want you to do is to unlearn everything that I taught in the last half an hour or so. Forget everything. Okay? It might seem like, a rigorous exercise. Follow these instructions. Bull. No. Don't follow instructions. While curve tracing, look at the function with deep love and affection. Not the kind you are imagining. A more puritanic variety of love. Now, because, if the order in which I wrote things, if you get very regimented with that, then it will only muddle you up. No, don't do all that. More or less, those are indicators. Those are things that you need to check. But don't have to check those things in that order. It will only create disorder if you did that. Don't do that. Right? So we'll avoid commotion. We'll get very simple with things that we have learned and try and trace curves commensurate. Okay? Say, I draw the curve of y equal to 1 by ln x. Say y equal to 1 by ln x. First of all, let me just draw the graph of y equal to ln x. All of you know this. This is the graph of y equal to ln x. at x equal to 1, it becomes 0. As x tends to 0 from the greater than 0 side, it tends to minus infinity, right? So, one thing, ln x had only, first of all, the domain of description was of ln x was x belongs to positive real numbers, right? This x belongs to positive real numbers, but to the exclusion of x equal to 1, because at x equal to 1, this will become undefined. Yes or no? So this would be, this and this, they differ in their domains. This includes x equal to 1, this excludes x equal to 1, right? Now, again, when x is less than 1, fx is negative, because ln x is negative. When x is less than 1, fx is negative, ln x is negative, so 1 by ln x will be negative. This is x equal to 1, right? As x tends to 0 from the greater than 0 side, ln x tends to minus infinity. Ln x tends to minus infinity. Do you realize that? So 1 by ln x would tend to 0. 1 by ln x would tend to 0. But while it's tending to 0, it will remain negative all the time, because ln x is negative, right? So as x tends to 0 from the greater than 0 side, 1 by ln x would tend to 0, but the graph of 1 by ln x would be below the x axis, because ln x is negative, right? Not only that, as x tends to 1 from the less than 1 side, ln x, 1 by ln x would tend to minus infinity. 1 by ln x would tend to minus infinity, isn't it? Right? If ln x in the interval 0 to 1 is monotonically increasing, then 1 by ln x would be monotonically decreasing, isn't it? As ln x increases, 1 by ln x decreases, right? You don't differentiate unnecessarily. So when I draw the graph from 0 to 1, there is no station, there is no local maxima minima that appears, because it's monotonic in this interval, right? And as x tends to, if I put all these things together, then this is what transpires. Yes or no? To the left of x equal to 1, this is the graph of y equal to ln x, right now? Now to the right of x equal to 1. Let's look at what happens to the right of x equal to 1. Okay. Now, as x tends to 1 from the greater than 1 side, 1 by ln x. See, ln x tends to 0, but 1 by ln x would tend to plus infinity. Why? Because to the right of x equal to 1, ln x is positive, so 1 by ln x would be positive. So 1 by ln x would tend to infinity plus infinity, right? So as x tends to 1 from the greater than 1 side, this tends to plus infinity. 1 by ln x would tend to plus infinity, and as x tends to infinity, this will tend to 0. 1 by ln x would tend to 0, right? And therefore, this becomes the graph of the function, right? This is the graph of 1 by ln x, therefore. So theoretically you can say that in this case, x equal to 1 is a vertical asymptote. X equal to 1 is a vertical asymptote. Even though x minus 1 does not explicitly appear in the denominator, but then notionally you can think of x equal to 1 as a root of this, and therefore x minus 1 to be a factor of this from remainder theorem. So that way you can also conclude that x minus 1 is a appearance in the denominator, right? This is why you get this. This is the graph of 1 by ln x. Makes sense? All right. Can I wipe this off? So far so good, right? Let me now trace, say, y equal to x square plus 1 by x squared minus 1. What appears blatantly, that should be the first thing you should register rather than doing things in the order in which I suggested. That order is rubbish. Okay? In this case, one readily available factors that x minus 1 and x plus 1 appear in the denominator. So x equal to 1 and x equal to minus 1 are two vertical asymptotes. Yes or no? Because x plus 1 and x minus 1 are factors of the denominator, right now? So 1 vertical asymptotes x equal to plus minus 1. X equal to plus 1 and minus 1 are two vertical asymptotes. That's one. The second thing readily available is what? Yes, only even powers of x. So symmetric about the y-axis. Only even powers of x. So even powers of x and therefore symmetric about y-axis. Right? Yes or no? Makes sense. Also, realize that y could have been written as 1 plus 1 by x squared, 1 minus 1 by x squared. Right? So, as x tends to plus minus infinity, y tends to 1. Right? As x tends to plus minus infinity, y tends to 1. Right? So, let me just state that somewhere. As x tends, that means as mod x tends to infinity, y tends to 1. That's evident from here? Yes or no? So let me draw the line y equal to 1. This is the line y equal to 1. That means when x becomes very large, the curve comes closer and closer to y equal to 1. Therefore, y equal to 1 should be looked upon as a horizontal asymptote. Y equal to 1 could be looked upon as a horizontal asymptote, right? Right. Now, let me see if there are critical points. Let me differentiate one time. Right? Dy dx is 2x into x squared minus 1 minus 2x into x squared plus 1 divided by x squared minus 1 whole square. Which is like 2x into minus 2, so that makes it minus 4x by x squared minus 1 whole square. Therefore, do you see that x equal to 0 is a critical point? The only critical point is x equal to 0 is a point where dy dx becomes 0. Now, When x is slightly less than 0, when x is slightly less than 0, what is dy dx? Positive. When x is slightly less than 0, dy dx is positive. When x is slightly greater than 0, what's dy dx? Negative. Yes or no? To the left of 0, dy dx is positive. To the right of 0, dy dx is negative. At x equal to 0, dy dx is 0. Therefore, x equal to 0 must be a local maxima. X equal to 0 must be a local maxima. Yes or no? First derivative confirmatory test towards a local maxima. How's that? Right? So, this is x equal to 0. This is x equal to 0. At x equal to 0, y is minus 1. At x equal to 0, y is minus 1. As you can see, y is minus 1. And you would see a local maxima here. So, just draw this indicative local maxima. Is it not? Huh? Okay. This is the only stationary point. This is the only turning point in the graph of the function. At all other points, it will be monotonic, either monotonically increasing or monotonically decreasing. Isn't it? Huh? Good. Now, so just to remove the clutter from here, can I wipe this off? So, we have discovered that x equal to 0 is a local maxima. Is a local maxima. Therefore, I just draw around local maxima something like this, and this is minus 1 because at x equal to 0, y is minus 1. Alright. Now, look, as x tends to 1 from the less than 1 side, y tends to minus infinity. Do you see that? Because x square minus 1 would be negative. When x is less than 1, x square minus 1 would be negative. Right? So, as x tends to 1 from the less than 1 side, y tends to minus infinity, right? Okay. So, now I am coming to, this is the line x equal to 1, right? This is the line x equal to 1. As x tends to 1 from the less than 1 side, y tends to minus infinity. Yes or no? Bolo bhai. Right? As x tends to 1 from the greater than 1 side, y would tend to plus infinity, right? Y tends to plus infinity. As x tends to 1 from the greater than 1 side, y tends to plus infinity. So, draw this, right? Yes or no? As x tends to 1 from the greater than 1 side, it will start to merge with the asymptote, right? And as x tends to infinity, as we have seen, as x tends to infinity, y tends to 1. So, as x tends to infinity, y will tend to 1. It will come closer and closer and closer and closer to 1 this way. Yes or no? Now, we have drawn the curve to the right of the y-axis. And we know that it's symmetric about the y-axis. All that we need to do is reflect this about the y-axis to draw the remaining part of the curve, right? It's symmetric about the y-axis owing to appearance of even powers of x, right? Right, very good. Reflect this portion about the y-axis, reflect this portion, the local maxima here. Right? Got me? This is all that we need to do. Are you fine with this? Right? This is the graph of y equal to x square plus 1 by x square minus 1. Do you understand all the spontaneous stages that led to drawing this trace? Right? Can I wipe this off? Now, let me illustrate a few things from the sheet that has been given to you. See, there is a problem which is y equal to x by 1 plus x squared. Y equal to x by 1 plus x squared. Let me draw the graph of this function. It has only one root, which is x equal to 0. Right? It has only one root, which is x equal to 0. X equal to 0. 0, 0 is the point of the graph of the function. Also notice that if x comma y be a point on the graph, then minus x comma minus y will also be a point on the graph of this function. Do you see that? Replace x by minus x, y will become minus y, isn't it? Nahi kya? Replace x by minus x, y will become minus y. Therefore, if x comma y is a point on the graph of the function, then minus x comma minus y will be a point on the graph of the function. Therefore, it will be symmetric about the origin and opposite quadrants. It will be symmetric about the origin and opposite quadrants. Right? Yes or no? Let me draw the graph of the function in the first quadrant. Let me draw the graph of the function in the first quadrant, and then we'll make, in order to make it symmetric in the third quadrant, we'll draw the graph commensurate with this requirement. Right? Let me draw the graph of this function in the first quadrant. That means for x greater than 0. So, for x greater than 0, see, one thing, y could be 1 by x plus 1 by x. Right? Hey, but this is a positive number and this is its reciprocal. It will always be greater than or equal to 2. A number plus its reciprocal, a positive number and its reciprocal will always be greater than or equal to 2. Yes or no? X plus 1 by x, arithmetic mean greater than or equal to the geometric mean for x greater than 0. Therefore, x plus 1 by x will always be greater than or equal to 2. Yes or no? Right? Therefore, this will always be less than or equal to half, because the denominator is always greater than or equal to 2. 1 by the denominator will always be less than or equal to half. That means y never exceeds half. For x greater than 0, y never exceeds half. And for x greater than 0, one thing, y will also be greater than 0. For x greater than 0, y will also be greater than 0. That means if the graph exists in the first quadrant, it will not exist in the fourth quadrant. In the first quadrant, see, for positive values of x, you are getting only positive values of y. Therefore, no part of the graph will exist in the fourth quadrant, because no positive value of x will give you a negative value of y. Right? Right? Okay. So, one thing, it has a maximum at x value equal to half. It has a maximum value equal to half. It has a maximum value equal to half, and that happens, this becomes equal to 2 at x equal to 1. Right? Y max is half. Do you see that? Y max is half. And it happens at x equal to 1. Right? So at x equal to 1, y max is half. And this is not just a global maximum. It's a local maximum also. It's a local maximum. Therefore, at x equal to 1, you would get a local maxima like this? Yes or no? Right now? Now, notice that y could have been written as 1 by x plus 1 by x. As x tends to plus infinity, y tends to 0. Right? As x tends to plus infinity, y tends to 0. And do you realize that there is no other turning point except x equal to 1? Isn't it? So as x tends to infinity, y tends to 0. And then draw the missing part. Yes or no? Now, because it's symmetric in opposite quadrants about the origin, and if the graph exists only in the first quadrant, then it will exist only in the third quadrant, right? And symmetry about the origin in the third quadrant will cause the graph to be something like this. Symmetric about this is x equal to minus 1. When x is minus 1, y will be minus half. Right? This is the graph of, and you know, like I said, one might just unnecessarily differentiate this and get the following. Say, you would get dy dx equal to 0 at x equal to plus 1 minus 1, but this time, there was no need to do that. But just a quick check. What is dy dx? dy dx is 1 plus x squared minus 2x squared by 1 plus x squared whole squared. Right? Which is 1 minus x squared by 1 plus x squared whole squared. dy dx is becoming 0 at x equal to plus 1 and minus 1. Plus 1 and minus, expected, na? And when at x equal to 1, dy dx is 0. When x is slightly less than 1, dy dx is greater than 0. When x is slightly greater than 1, dy dx is less than 0. So x equal to 1 ought to have been a local maxima. But did I actually need to check this using differentiation? No. But you could have. You could have. Right? Once I know the turning points, I actually don't have to separately check whether the function is monotonically increasing or decreasing, because there are only exclusive options that you are left out with to draw the curve given the local maxima and local minima. To the left of a local maxima, you will know that it's monotonically increasing. To the right, it will be decreasing. Don't have to break your heads too much. If there is a local maxima and a local minima, there must be a point where in between a local maxima and local minima where d2y dx2 becomes 0. And that will be a point of inflection. In this case, see, x equal to 1 is a local maxima, x equal to minus 1 is a local minima. Even without differentiating a second time, can you tell me what should have been a point of inflection? X equal to 0 should have been the point where the curve changes shape, x equal to 0. From symmetry considerations, right? Don't differentiate a second time here unnecessarily to find d2y dx2 is 0 at x equal to 0. You know that that's the only possibility where it transits from concavity to convexity or vice versa. Right? All of you understand this, isn't it? Huh? Simple, right? Can I wipe this off? Huh? Is this understood by all? Let me draw another one for you. From the sheet, let me trace y equal to 1 plus x squared minus x power 4 by 2. Let me trace the graph of 1 plus x squared minus x power 4 by 2. Only even powers of x. Symmetric about the y-axis. Right? So one thing, it's symmetric about the y-axis. Which means if I just draw the curve for x greater than 0, then that's enough. Then I can reflect the curve about the y-axis to get the curve for x less than 0, right? So let me just draw the curve for x greater than 0. But the first thing that I want to do here is, let me find the roots of this. Values of x for which y becomes 0. Let me find the roots. It's a quadratic in x squared, right? So x squared would be minus b plus minus root squared plus 4ac by 2a, which is minus 1. Right? Yes or no? Which is minus 1 or 1 plus minus root 3. Hey, x square cannot be 1 minus root 3. Because 1 minus root 3 is negative. 1 minus root 3 is negative. It cannot be square of x. X is a real number. So the only possibility is x square must be 1 plus root 3. Right? Therefore, the two roots would be x equal to plus minus root 1 plus root 3 must be the two roots of this. This equation has two real roots and two complex roots. These are the two real roots. When we are plotting, we need the real roots really. Right? These are the two real roots. Right? So x equal to, let's say the positive real root is root 1 plus root 3 is the positive real root of this function. Clear? Now, let me check for critical points dy dx. Right? The critical points are dy dx is 0 at x equal to 0 and plus minus 1. Right? When x is 0, dy dx is 0. Right? When x is slightly less than 0, dy dx is negative. See? When x is slightly less than 0, dy dx will be negative. When x is slightly greater than 0, dy dx is positive. Therefore, x equal to 0 must be a local minima, right? X equal to 0 must be a local minima. Very good. And the value of y at x equal to 0 is 1. So at x equal to 0, the value of y is 1 and it must encounter a local minima. It must encounter a local minima. Draw this bowl, downward bowl like this to demonstrate a local minima at x equal to 0. Right? Now, x equal to 1 will be somewhere here between this and this. Right? See, I can, even without doing hanky-panky, x equal to 0 is a stationary point, x equal to 1 is a stationary point. If x equal to 0 is a local minima, I am guaranteed that x equal to 1 will be a local maxima. Local minima and maxima occur alternately. Right? So if x equal to 0 is a local minima, x equal to 1 will be a local maxima. So expected, see, because after x equal to 0 it's increasing, so you would expect a local maxima, right? So you expect a local maxima at x equal to 1, and then after a local maxima there is no further turning points, it will just go down and down and down to the deep from whence it sprung. Right? And it encounters a root which is root 1 plus root 3, right? That was the root. That was the root. That's a graph to the right of y-axis. But it's symmetric about the y-axis, so reflect it. It's symmetric about the y-axis owing to occurrence of even powers of x. So reflect the same thing as accurately as you could. This must be minus 1 and this must be minus root 1 plus root 3. Right? That's the trace of y equal to 1 plus x squared minus x power 4 by 2. Isn't it? Got me? Sounds fine, right? Oh, okay. Few things readily observable. What are the three roots? Minus 1, 2, 2 are the three roots of this, isn't it? 2 is a repeated root. So roots are minus 1, 2, 2 are the roots. Hey, remember this? If x equal to alpha is a root repeated k times for a polynomial, then for its derivative it will be a repeated root repeated k minus 1 times. That means dy dx must become 0 at x equal to 2. Because x equal to 2 is a repeated root of this, repeated twice, then x equal to 2 would be a single root of the derivative function. Would be a single root of the derivative function. Has to be the case. Check that. Dy dx is x minus 2 whole squared plus 2 into x plus 1 into x minus 2, which is like a x minus 2 into x minus 2 plus 2 into x plus 1 3x. That's dy dx, right? Right? So one thing, the roots are minus 1, 2, 2. Hey, when x is slightly less than 0, what is dy dx? When x is slightly less than 0, this is also negative, so dy dx is positive, right? When x is slightly greater than 0, this will be positive, this will be negative. Therefore, dy dx will be negative. That means at x equal to 0, dy dx is 0. To the left of x equal to 0, dy dx is positive. To the right of x equal to 0, dy dx is negative. It must be a local maxima. X equal to 0 must be a local maxima, right? So, and the value at x equal to 0, as you can see, is 4. 4 is the value of the function at x equal to 0. And it has a local maxima, right? And do you see that for x greater than 0, this is always greater than or equal to 0? That means now in the first quadrant, no part of the, for x greater than 0, that means to the right of the y-axis, no part of the graph will be below the x-axis, because y is never getting negative. And x equal to 2 is another stationary point. If x equal to 0 is a local maxima, x equal to 2 must have been a local minima, without the graph falling below the x-axis. And then after 2, no more turning points. After having encountered a local minima, it's keeping to go up and up and up. right? This is the graph in this, right? Yes or no, right? Okay. Now, no more turning points, no more turning points. So we turn around and say, all right, from this point, it will encounter a root at x equal to minus 1, encounter a root at x equal to minus 1, go this way, because it's not turning after this, so it will follow the same direction. See, again, if you're stupid, you would differentiate and check where the function is increasing or decreasing, but in this case actually there is no need. If you know that there is no further turning point, then it must exhibit monotonicity. So don't differentiate one more time and check where it's increasing, where it's decreasing. This is it. This is the graph of y equal to x plus 1 into x minus 2 whole squared. This much, right? Can I wipe this off? Y equal to 1 by 1 minus x squared. Okay. Two asymptotes, plus 1 and minus 1. Two vertical asymptotes, x equal to plus 1 and x equal to minus 1 for this function. And only even powers of x. Therefore, symmetric about the y-axis, right? At x equal to 0, the value of the function is 1. At x equal to 0, the value of the function is 1. Right? Now, check this dy dx. Yes or no? Right? When x is less than 0, dy dx is minus 2x. Minus 1 by minus 2x plus 2x, sorry. When x is less than 0, dy dx is negative. When x is greater than 0, dy dx is positive. Have I differentiated it right? Minus 1 by 1 minus x squared whole squared to minus 2x. Yeah. Right? Right? So when x is less than 0, dy dx is negative. Right? When x is greater than 0, dy dx is positive. Although I didn't expect this to happen because oh yeah. That's why, because I was, if it was a local maxima, then it would go this way and it would have had roots. That's why I was messed up. I by mistake wrote 1 here, 1 would be a point there. I'm so sorry about that. Because See, I tell you why I didn't think this was right. Because if there was a local maxima here, as this designates, then this would have had a root. But this doesn't have a root. See, 1 by 1 minus x squared is not becoming 0 for any value of x. Therefore, this was all turning out to be inconsistent. Just because I wrote this 1 by mistake here, x equal to 0, now this seems all right. So, x equal to 0 must be a local maxima. Now it's fine. Now it seems good. X equal to 0 must be a local maxima. Therefore, if it's a local maxima, it's like this. And do you realize that this is the only turning point? This is the only turning point, isn't it? Local minima, local minima, local minima. Local minima, sorry, local minima. I'm so sorry, I'm so sorry. It's a local minima. It's a local minima. I apologize for this. X equal to 0 is a local minima. X equal to 0 is a local minima. Now, as x tends to 1, from the less than 1 side, do you realize that y tends to plus infinity? As x tends to 1 from the less than 1 side, y tends to plus infinity, right? Without any more turning points, because this was the only turning point, x equal to 0, a local minima, right? And as x tends to 1 from the greater than 1 side, y would tend to minus infinity. Do you see that? As x tends to 1 from the greater than 1 side, y would tend to minus infinity, right? So, as x tends to 1 from the greater than 1 side, it will tend to minus infinity, and as x tends to infinity, y would tend to 0, right? As x tends to infinity, y would tend to 0, right? Therefore, if you put it all in perspective, then this becomes the graph. But it's symmetric about the y-axis. So, whatever you have drawn to the right of the y-axis will get reflected about the y-axis, this portion and this portion. This becomes the graph of y equal to 1 by 1 minus x squared. Yes or no? Y equal to x power 4 by 1 plus x whole cubed. All right. Do you see some roots here? 0 is a root. Repeated 4 times. So its dy dx must also become 0 at x equal to 0, right? So you perhaps in for either a local maxima or a local minima at x equal to 0. We'll check that out later, right? Then, do you see an asymptote? X equal to minus 1. Right? Let's differentiate this with respect to x, right? And examine for x equal to 0. Right? See, 4x cubed into 1 plus x whole cube minus 3 into 1 plus x whole squared into x power 4, isn't it? So, I could, let's say, take x cubed common from this, x cubed common from this, and 1 plus x whole cubed could be cancelled from numerator and denominator. 1 plus x whole squared could be cancelled. So this will become 3x power 4. So this will become x power 4, right? 1 plus x whole squared cancel. So x cubed 4 into 1 plus x minus 3 divided by 1 plus x whole to power 4. minus 3x, sorry, minus 3x. So which is like x cubed into x plus 4 divided by 1 plus x power 4, right? Now, dy dx is becoming 0 at x equal to 0 and at x equal to minus 4. Now, what about x equal to 0? When x is slightly less than 0, this will be negative. When x is slightly greater than 0, it will be positive. So, x equal to 0 must be a local minimum. X equal to 0 must be a local minimum, isn't it? Right? X equal to 0 turns out to be a local minimum. And then, even without checking, you can say x equal to minus 4 must be a local maximum. Local maximum, right? Now, let's start putting it all in place. This is the asymptote x equal to minus 1. This is the asymptote x equal to minus 1, right? Do you also see that as x tends to minus 1 from the greater than minus 1 side, y tends to plus infinity? Y would tend to plus infinity? That means you would expect this to happen. At x equal to 0, not only is y 0, but dy dx is also 0 at x equal to 0. And we have seen that at x equal to 0, see, if it is coming this way, then we actually expect a local minimum at x equal to 0, right? A local minimum at x equal to 0. And then after 0, there would be no turning point. So it will go this way, right? Okay. Now, x equal to minus 4 is a point here, right? At x equal to minus 4, y is negative. At x equal to minus 4, y is negative. So, y is somewhere here. And not only that, it has a local maximum at x equal to minus 4. So, you would expect something like this. At x equal to minus 4, a local maximum. Yes or no? Right? Now, as x tends to minus 1 from the less than minus 1 side. As x tends to minus 1 from the less than minus 1 side, do you realize that y would tend to minus infinity? Right? Right? Yes or no? Now, given this, let's see if there are asymptotes to the curve that are inclined. This was a vertical asymptote x equal to minus 1. To refine the curve, let me check if there are inclined asymptotes to the curve. But this seems all right, right? This seems all right. So far, so good, right? Now, can I wipe this off? Can I wipe this off? Say there is an inclined asymptote. Which is y equal to mx plus c. And if you remember, if that be this is y equal to fx, then if an m exists, then m must be limit fx by x as x tends to, let's say, plus minus infinity. That must be the slope, right? Fx by x means x cubed by 1 plus x whole cubed as x tends to plus minus infinity. And what is this limit equal to? 1. You divide by x cube numerator and denominator, you will get this limit as 1. So m turns out to be 1. Right? What would fx be? Fx would be, what would c be? C would be limit x tends to infinity fx minus mx. Fx minus mx. Right? So if there exists a c, then that c must be limit fx minus mx as x tends to plus minus infinity. Yes or no? Which is to say, c must be limit fx, which is x power 4 by 1 plus x whole cubed minus x as x tends to infinity plus minus infinity, as x tends to plus minus infinity. M is 1 here, isn't it? What is this limit? X power 4 minus x into 1 plus x whole cubed divided by 1 plus x whole cubed, x tends to plus minus infinity, right? X power 4 will get cancelled, so you will have minus x into 1 plus 3x plus 3x squared divided by 1 plus x whole cube as x tends to plus minus infinity, right? Isn't it? Now, if you divide both numerator denominator by x cubed, if you divide numerator denominator by x cubed, what would you get? Limit 1 minus of 1 by x squared plus 3 by x plus 3 divided by 1 by x plus 1 whole cubed as x tends to plus minus infinity, right? Which is minus 3. C turns out to be minus 3, as you can see. Right? So there is an inclined asymptote, and the inclined asymptote for this curve, is y equal to x minus 3. X minus 3 is the inclined asymptote. Now let's refine this curve. This was good enough, but let's get a superior look of the curve. So let me first draw the two asymptotes and redefine this, refine this, the looks of the curve. Okay, but so far so good. I hope all of you have understood these calculations here, right? Let me first draw the two asymptotes and redraw this curve. Y equal to x minus 3 is this asymptote. C is minus 3. This is y equal to x minus 3. Is an asymptote. As x tends to plus or minus infinity, the curve tends to y equal to x minus 3, right? There is a vertical asymptote, which is x equal to minus 1 is a vertical asymptote. Okay. Now everything else remaining the same. We will not redo our calculations. Let me draw the curve. See, it's going this way, beautifully merging with y equal to x minus 3 in the long run, right? And x equal to minus 4 must be somewhere here. Again, as x tends to minus infinity, y tends to x minus 3. So this must be x equal to minus 4, a local maxima. A local maxima at x equal to minus 4. This is a refined look of the same curve. What do you say? है ना? Got me? Let's draw the next one. Clear, no? Y equal to 2x minus 1 plus 1 by x plus 1. Okay. Very readily, what are the two things you could say? Right, right. X equal to minus 1 is a vertical asymptote and 2x minus 1 is a inclined asymptote. Right, let's first do that. What's readily available? X minus 1 must be something like this, right? This must be y equal to 2x minus 1. And this must be x equal to minus 1. A vertical asymptote. This much at least, right? Now let me find the roots of this. Let me find the values of x for which y becomes 0, right? 2x minus 1 into x plus 1 plus 1 will be 0 for roots. These would be the values of x for which y becomes 0. So this is like 2x squared plus 2x minus x plus x equal to 0, or x into 2x plus 1 is 0, x equal to 0 and minus half. Yeah, x equal to 0 and minus half are the roots, right? Did you get this? 0 and minus half are the roots? Yes or no? So this is x equal to 0 and say x equal to minus half will be somewhere here. X equal to minus half will be somewhere here. These are the two roots, right? Now few things very readily. Can I remove this? 0 and minus half are the roots. So one thing, between 0 and minus half I would either expect a loop like this or I would expect a loop like this. Yes or no? Which means between 0 and minus half I would expect at least a local maximum or at least a local minimum. Yes or no? Isn't it? Now as x tends to minus 1 from the greater than minus 1 side. Okay? This tends to plus infinity. This tends to plus infinity and this will be a finite number. So the whole thing tends to plus infinity. Right? The whole thing tends to plus infinity, which means you would expect something like this. Right? Yes or no? And therefore, chances are that even without doing too much, I can say that if this must be going this way, and a local minimum, and must be going this way. Can I say that? Even without differentiating, I'm expecting between minus half and 0 a local minimum. A local minimum is what I'm expecting between minus half and 0. Right? And as x tends to minus, so as x tends to minus 1 from the greater than minus 1 side, y tends to plus infinity. As x tends to minus 1 from the less than minus 1 side, from the less than minus 1 side, this will tend to minus infinity. This is a finite number, so the whole thing will tend to minus infinity. So I would expect something like this. And this again being an asymptote, I would expect a local maximum to appear somewhere here. So I would expect, See, I would expect a local minimum here and I would expect a local maximum. A local minimum to the right of minus half and to the left of 0, and a local maximum to the left of minus 1 is what I'm expecting in this graph. Are you okay with this? Huh? Let's differentiate to just confirm our understanding. dy dx is 2 minus 1 by x plus 1 whole square. Right? dy dx will be 0 when 1 plus x whole square is a half, or 1 plus x is plus minus 1 by root 2, or when x is, so dy dx is 0 when x is minus 1 plus minus 1 by root 2. Hey, minus 1 by root 2 must be to the left of minus 1. That means, you know, this must be minus 1 by root 2 where you would expect a local maximum, and minus 1 plus 1 by root 2 must be here. See, one thing, minus 1 plus 1 by root 2, minus 1 plus 1 by root 2 is like minus 1 plus 0.7, roughly 0.7. So, minus 0.3 roughly, minus 0.3 is obviously between minus half and 0, isn't it? So, I would expect a local minimum here, I would expect a local maximum there, and therefore, putting all of this in place in one shot at x equal to 0, this is what I would expect, right? And on this part at minus 1 by root 2, I would expect something like this. This is minus 1 by root 2. I would expect a local maximum, right? This is the graph of the function, isn't it? Complete graph of the function. Hello. Let me look at the next one. Y square is x power 4 into x plus 1. Okay, very quickly, what are the things that you can, 0 and minus 1 are the roots. And 0 is a repeated root. How to? কি খোকা এই মালটা শেষ হয়ে যাচ্ছে মাইনাস 1 এ 0 একটা রুট এর জন্য x equal to 0 একটা রুট right now there are two roots in fact y equal to x squared plus minus x squared root x plus 1 so minus 1 okay now even powers of x even powers of y so symmetric about the x axis. Also, when x is less than minus 1, y square will become negative. So, x less than minus 1 is not possible because for x less than minus 1, this number becomes negative, but y square cannot be negative. That means the graph does not exist to the left of minus 1. The graph does not exist. That means will exist from x equal to minus 1 to the right. only. Will not exist to the left of minus 1. Right? These are some very simple, readily available conclusions. No part of the graph will exist to the left of minus 1. There is a root at minus 1, there is a root at 0. You would therefore expect a loop here and a loop here because of symmetry about the x-axis. Right? So in any case, between minus 1 and 0, you would expect a turning point. Right? Isn't it? If there is a loop, at least one turning point between minus 1 and 0 is what you will expect. So let's differentiate. Let's differentiate to examine a critical point, a turning point. Dy dx, 2y dy dx, 4x cubed into x plus 1 by plus x power 4, which is like x cubed into 4 into x plus 1 plus x, which is x cubed into 5x plus 4. Dy dx is becoming 0 at x equal to 0 and at x equal to minus 4 by 5. And x equal to minus 4 by 5 is indeed a point here. Right? And can I then say that at x equal to 0, you would expect something like this. And because of symmetry about the x-axis, you would expect something like this. Dy dx again becoming 0 at x equal to 0. Right? And then, as x becomes larger and larger, y would become larger and larger. It will take up shape like this. Go this way. Yes or no? Got me, na? See, as x tends to infinity, then y tends to infinity. As x tends to infinity, y tends to infinity. This would be the shape of the curve. Let me draw this. One minus x to power 2 by 3 whole to power 3 by 2. Even powers of x. Symmetric about the y-axis. And this could have been written as y squared is 1 minus x to power 2 by 3 whole to power 3. So symmetric about the x-axis also. It's symmetric about both axes, x-axis and y-axis, right? I hope you realize why I said this. Right? Because when you square, you get y squared is 1 minus x to power 2 by 3 whole cube. So even powers of y. In fact, no. It's symmetric only about the y-axis. Because, see, I don't have the luxury, I don't really have the luxury to square and get an even power of y. See, when I square, I am forcing an even power of y, but which is not the case. So I can't square. That will be unnecessarily creating symmetry about, see, when I have a line y equal to x, I can't say y squared is x squared and even powers of y is so symmetric about the x-axis. I can't say this, isn't it? So I can't square and say that it's symmetric about the x-axis. All that I can say is it's symmetric about y-axis. Why? Because there are even powers of x. Because there are even powers of x. Yes or no? Also, do you realize that x must lie between -1 and +1 only? Because x to power 3/2 must lie between -1 and +1. I mean, in the sense, x to power 2/3 must be less than 1, must be numerically less than 1. Yes or no? Because you have a square root there. So this can't be greater than 0. This can't be greater than 0. Yes or no? This can't be less than 0. I'm so sorry. This can't be less than 0. So for sure, x must lie between -1 to +1 only. X must lie from -1 to +1 only. Right? Let me draw the graph only in the first quadrant, because then I can reflect it about the y-axis. So for x greater than 0, it also has to be less than 1. For x greater than 0, it also has to be less than 1, because 1 minus this has to be greater than 0, because 1 minus this has to be greater than 0, right? So if this has to be greater than 0, why? Because there is a square root sitting there. You can't make this number negative. And for this to be greater than 0, x must be less than 1. Yes or no? Because if x is greater than 1, then x to power 2/3 will be greater than 1. This will become a negative number, and then you can't find a real square root of that. Right? So x has to be less than 1 if it is greater than 0. Right? So in the first quadrant, the graph exists. In the first quadrant, the graph exists only between 0 and 1. Only between 0 and 1. At x equal to 0, y is 1. At x equal to 0, y is 1. At x equal to 1, y is 0. Right? So these are 2 points on the graph. Now, between these two, you could either have something like this, or you could have something like this. Right? Let's see what happens. So for that, we need to differentiate with respect to x. We need to differentiate with respect to x. So if I differentiate with respect to x, this is what I get, isn't it? -1/3. Sorry. -1/3. Right. This is what I get. Right. Now, see, at x equal to 1, dy dx is becoming 0. At x equal to 1, dy dx is becoming 0. So would you realize that at x equal to 1, it's going this way? And that's the only value of x where dy dx is becoming 0. And y is positive for x lying in the interval 0 to 1. Y is always positive. Do you realize that? Y is always a positive number here. Therefore, at x equal to 1, dy dx is becoming 0. So you would expect something like this here. And therefore, in line with this, you would expect something like this to happen between 0 and 1. Yes or no? And at x equal to 1, at x equal to 0, see, this will come in the denominator. X to power 1/3 will come in the denominator. Dy dx tends to infinity as x tends to 0. Right? See, which is what is happening. See, this could be written as -1 minus x to power 2/3 whole to power half divided by x to power 1/3. See, as x tends to 0, dy dx tends to plus infinity. Isn't it? See, which is what it is. As x tends to 0, dy dx is becoming vertical. Plus infinity is vertical, isn't it? So which is what it is. Which is how it's, right? Yes or no? And it's symmetric about the y-axis. Why? Because even parts of x. And therefore you would expect something like this. Which part? See, dy dx is 0 at x equal to 1. 0 at x equal to 1. At x equal to 0, realize that it's minus infinity. Very large. Dy dx is very large at x equal to 0. That means very large dy dx means very large slope of the tangent, means a vertical tangent at x equal to 0. The tangent at x equal to 0 is purely vertical therefore. And then it enjoys symmetry about the y-axis. Why? Because there are even powers of x, and therefore this would be the trace. What do you say? Right? This would be the graph of y equal to this. However, if someone said, draw the graph of y squared equal to 1 minus x to the power 2/3 whole to power 3 by 3, then it will be the same except that this would get added. If someone said, draw the graph of this, then it would also be symmetric about the x-axis because there are even powers of y, and in addition to these two, this will also get added. This will also get added. Got me now? No? Right? So far so good, right? Readily, what can you say? There are two, yes. Right away you say the asymptotes. There is an inclined asymptote which is y equal to x, isn't it? And there is a vertical asymptote which is x equal to 0, which is the y-axis, isn't it? X equal to 0 is a vertical asymptote and y equal to x is an inclined asymptote. Let me first draw the asymptotes. This is y equal to x, an inclined asymptote, and the y-axis is also an asymptote, right? Isn't it? Now, what is dy dx? See, there are no roots of this because x square plus 1 will never be 0. So, no roots, no real roots, that is to say, of this. Dy dx is 1 minus 1 by x squared, and dy dx becomes 0 at x equal to plus minus 1. Dy dx will become 0 at x equal to plus minus 1. Now, see, as x tends to 0 from the greater than 0 side. As x tends to 0 from the greater than 0 side, this will tend to plus infinity, this will tend to plus infinity. So, the whole thing will tend to plus infinity. And while doing so, it will encounter a turning point at x equal to 1, right? It will encounter a turning point at x equal to 1, it will turn around and flush with y equal to x in the long run. This is what it will do, right? In fact, we could have said x plus 1 by x for x greater than 0 is always greater than or equal to 2. At x equal to 1, therefore, we would have expected a minimum value of this, isn't it? So, even without differentiating, we could have said that, well, okay, this length is 2 units at x equal to 1, right, Aditya? Huh? One more thing. If you replace x by minus x, y becomes minus y, isn't it? If you replace x by minus x, y becomes minus y. Therefore, if x comma y is a point, minus x comma minus y will also be a point on the curve. And therefore, it's going to be symmetric about the origin in opposite quadrants. Symmetric about the origin in opposite quadrants. And this is where you see this other point minus 1 where dy dx becomes 0. This is the trace. Right? This is the trace of x plus 1 by x. Got me now? Yes, please. Haan, bolo. Haan. You have a class. Okay. Wait for one more problem after this. Let's draw the graph of this. I could write it like this, isn't it? X plus 2 minus 1 by x, 2 asymptotes. Y equal to x plus 2 and x equal to 0. That means the y-axis is an asymptote, right? The two asymptotes are, one is x equal to 0, which is the y-axis, and the other one is y equal to x plus 2, which is an inclined asymptote. So let me first draw the asymptotes. The y-axis, which we anyways have to draw. This is an asymptote. Y equal to x plus 2 is this line. Right? What is dy dx? 1 plus 1 by x squared, which is positive for all x. Which is positive for all x. That means the function is, wherever defined, it's only increasing. Right? And as x tends to 0 from the greater than 0 side, as x tends to 0 from the greater than 0 side, this minus 1 by x will tend to minus infinity. So y tends to minus infinity, yes or no? As x tends to 0 from the greater than 0 side, right? Therefore, greater than 0 side, y tends to minus infinity. No other turning point, it's going to go on increasing. It goes on increasing, does this, boom. This is how it goes. And therefore, you would expect one root of this somewhere here, which you can obtain by x square plus 2x minus 1 equal to 0 will give you two roots, one positive and one negative root. Why? Because the product of the roots is negative. So the positive root is obtained here. So one root will be positive, the other root will be negative. Yes or no? As x tends to 0 from the less than 0 side, y will tend to plus infinity. So we'll expect something like this. And this being the asymptote, we would, in order to produce monotonically increasing behavior, this is what would happen. And this would be the second root. These are the two roots, alpha and beta, of the numerator of this. This will be the graph of x squared plus 2x minus 1 by x, isn't it?